Hi everybody, very sorry for the prolonged delay. This is part 2 of the Riddle short introduction. We'll be touching on interstellar scintillation and a few other topics today. So why are we interested in this stuff anyway? One of the things that is of interest to us should be self-interest. Surely as we pass through the interstellar medium, there is cosmic ray variability. That changes over time. And that influences cloud cover, lightning intensity, surface mutation rates, which is one of the fancy ways of saying cancer, affects evolution, etc., and so forth. It also affects and changes biomarker strength. And essentially what this boils down to, whether one is looking for future habitable planets or our present planet Earth, what it boils down to is galactic cosmic rays and even stellar cosmic rays in terms of those M-dwarf stars and young planets. For example, just as we have CMEs here, which could potentially erode a planetary atmosphere, active M-dwarf stars may erode a planetary atmosphere for a young planet with dense and fast stellar winds as well. So clearly for life to develop habitable conditions, those conditions have to be maintained for sufficiently long time scales. And of course, more modeling of atmospheric escape, for example, is necessary to gain a better understanding. So whether it's galactic cosmic rays and considering their variability vis-a-vis the interstellar medium, or whether it's stellar cosmic rays and relatively young planets, we want to understand how the biomarker molecules of terrestrial exoplanets are affected. Perhaps the most important self-serving reasons to understand the local interstellar medium is because we have to understand how the interstellar medium can compress our heliosphere. For example, it's relatively easy if you change the density from even by a factor of 50, you can literally decrease the heliosphere from out to 100 AU to down to 10 AU. And some of the things that could happen as a result of that would be cosmic ray ionization into the lower atmosphere, which would essentially increase cloud cover and directly affect the temperature. Of course, there is argument about that currently, but I lean towards the research that shows that that would probably dramatically drop temperature on our planet. And of course, lightning triggered by cosmic ray secondaries is substantial as well. Cosmic rays also increase various atmospheric chemicals that will directly alter our ozone as well. And one of the other significant things is cancer rates, DNA mutation, and so forth. And let's not forget one of the worst case scenarios, which would be a direct deposition of interstellar medium materials onto our planetary atmosphere, which would likely result in a snowball Earth. Alright, so this is going to be the shortest crash course in studying the local interstellar medium that you will literally ever take in your entire life. So how do we go about measuring this stuff anyway? Well, there's a couple ways to do it. We can use radio astronomy to study the line of sight. We can use absorption line spectroscopy. We can take in situ measurements such as the missions Ulysses through IBEX to determine properties in the local interstellar medium. Some of the key things we're going to be interested in to do that is essentially the global morphology, the kinematics, and intercloud variation of the local interstellar cloud and the other clouds in the line of sight. And again, that will help us determine temperature, turbulence, everything that you see on that graph. And that's pretty gosh darn important, and we'll get to that in a second. I think it's fair to say that most of us understand that space is not empty, and that all signals from astrophysical sources travel through ionized media before they reach Earth. And despite seeming empty, the space between the stars and our Milky Way galaxy is actually filled with a low-density gas called the interstellar medium, which is why you might see ISM on some of these cards here, slides, I guess. So it'll say, for example, ISM, interstellar medium, LISM, local interstellar medium, and you might see a few more variations, which we'll cover later. So anyway, stars form from this material, and when those stars die, they replenish it with elements heavier than the original hydrogen and helium. When stars explode, aka supernova, the gas is disturbed and irregularities do form. And these new features are important in the formation process for the next generation of stars. Knowing more about the properties of the interstellar medium allows for, of course, a better understanding, again, of our evolution, stellar evolution, and galactic evolution. And one of the ways that properties of the interstellar medium can be studied is by looking at the radio waves produced by a pulsar. Don't have a heart attack, everybody. Pulsar is really no big deal. A pulsar is a neutron star that contains 1.4 solar masses packed into a sphere approximately about 20 kilometers in diameter that spins very rapidly. So, just as a lighthouse might sweep out a path of light as it rotates, a pulsar simply has a similar beam of radio emission. That's not too bad, is it? And these beams are thought to be related to the strong magnetic field of the pulsar and are emitted from the poles. Pretty cool, huh? So as the beam crosses the line of sight, a pulse is seen. And on average, these pulses tend to be very stable shapes from the pole. And we can use those to help us figure out things about the interstellar medium. So moving along, by measuring the variations with time in the delay, we can measure electron density variations in the interstellar medium. And the second measurement is interstellar scintillation. The variable density of the ISM disrupts the phase of the pulse radio signal, so we get constructive and destructive interference of the wavefront, which results in an interference pattern through which our planet, the Earth, moves. This is seen as a variation in time of the intensity flux of the signal. And lastly, there's interstellar scattering, and this affects the shape of the pulse signal to broaden as it is scattered through the medium. And the random density of the interstellar medium causes that signal to travel many different paths as they are refracted. And when a signal takes a bent path, it travels a longer distance to the telescope, and therefore the signal will arrive later. So anyway, we average over all paths taken the approximate effect of the convolving the intrinsic pulse with an exponential decay of scattering timescale. And the value of that time scale is going to depend on the radio frequency and the statistical properties of the medium through which the signal traveled. These three quantities vary with time, and it is these variations, when you compare models that allow us for probing the properties of the interstellar medium. And these models do show us that turbulent interstellar medium does exist. So very long story short, we can take some basic measurements that help us determine the general interstellar medium properties close and in 3 dimensions, such as what I mentioned earlier, morphology, kinematics, phase interaction, ionization structure, and so forth. And here are some of the things that have been determined so far based on that. So here is a very rough breakdown of some of the immediate concerns that are being thought about and theorized about at this time. There seems to be a growing consensus that the Sun is currently located in transition material between 2 clouds, If you want to go more in depth about that, please refer to the first video. Also, there is a compression of warm clouds that are creating cold clouds and filaments. And radio scintillation seems to be indicating that, as well as other measurements that have been taken. In addition, when looking at the global kinematics of some of the clouds in our line of sight, it was initially thought that there was a number of clouds in a simple single velocity flow. However, a few things have been detected. One of them seems to be some separate dynamical clouds. And of most significance is a deceleration at the leading edge of the local interstellar cloud. Theoretically, this could either indicate that there's possibly some sort of leading edge that is running into denser material, and usually denser material suggests cold cloud material or filaments. And again, if you want to look into that some more, look at the first video. Or it could certainly just be turbulence. And I know that, or I've read that Frisch believes that it's just simply turbulence, while others not so much. So that is, again, another issue that's being thought about. Most dynamical clouds, incidentally, have filamentary structures, possibly due to collisional interfaces. So that's why when you look at the flow of clouds among the sight lines, that's a important issue, because again, when these filaments come into being, they're very, very small, and we could very well be on top of a filament or a cloudlet and really have no indication of that until it's beginning to happen. With regards to cold clouds, such as the Leo cloud, as our tools get better and as we learn more along the way, scientists will be able to do more to determine just exactly where these cold clouds are, and hopefully get down to being able to measure these very small filaments and cloudlets that are very difficult to see at the current time. However, based on the evidence, such as the slowing down of clouds more towards that direction, and some of the cloud-cloud interaction that's being determined by interstellar scintillation, there is some indication that that is going to be something that is going to have to be dealt with in the future, probably sooner than later. Although there has been talk in the past about that sort of thing being a concern in several thousand years, that timeline has been reduced, and I do expect that to be reduced further as technology develops to be able to see further. Finally, just as with many other things, studying balance is important. There has to be a balance between our heliosphere and the local interstellar medium. The local interstellar medium essentially defines our heliosphere, and the Voyagers crossing the termination shock and the IBEX mission are making great leaps in our scientific knowledge of that. So, again, over time, science will delve into these issues. We will learn a lot more. But keep in mind that the local interstellar medium, that is our local community, in essence, of the interstellar medium around us, does and can affect planetary atmosphere, and has done so in the past and will do so in the future. Thank you for tuning in. And I'm sorry, I'm not going to hit interstellar dust today. I'll pick that up very quickly in the next video, and we'll be getting into the cycles that I showed you the slide about earlier, and talk about galactic grand cycles as well. Thank you. Goodbye.